ROS developers, and welcome to a new open class. Yes, we are back with open classes again. And today we are going to be talking about ROS2 and more specifically about executors and callback groups. So we are going to see a little bit, we are going to scratch a little bit what are these for and how they are used in ROS2. So yeah, we are today in open class number 149. So welcome everybody. I hope everything is fine, sound is good, image is good. I am checking here in my laptop and everything seems okay. In any case, if there is something wrong, please let me know in the chat. I'm going to be reading your comments there. So yeah, then let's get started. I'm going to start sharing my screen right now so that I can have access directly here to the chat and everything. So let's come here, and then as always I'm going to start here by logging in, and let me come here to the class. Yeah, there we go. Okay, so yeah, image, sound seems to be okay. I don't see any chat messages for now. Okay. Then, yeah, so let's get started. Then, as always, let me just remind it in case that there are any newcomers to this class. So the first thing that we need to do before starting with the class is to get the class rosject. Yeah, the rosject is a project which contains all the files and setup that you're going to need in order to follow today's class. All right. Then in order to get this rosject, what you have to do is to click here in this light blue button on top of the chat, which says fork and open the class rosject. I'm going to do it myself here. So let me click it. And then this is going to create a copy of this rosject into your account. So you are going to have this rosject forever for you. And as you can see, it also automatically opens the rosject. This might take some seconds, even one, maximum a couple of minutes to fully load. So, so yeah, all of you, please do this, okay, right now. Click on this button and access today's rosject, because here you're going to find the notebook with all the instructions, as you can see right now. Yeah, so mine is opening here many things by default because it saves the previous configuration. But yeah, in your case, you should you're going to get this this notebook, automatically opened. As you can see, this Jupyter notebook for today's class, which is number 149. We are going to talk about executors and callback groups with ROS2. And yeah, this notebook basically contains all the instructions that you need, the pieces of code that we are going to be creating, commands that you are going to use, etc. Okay, so important that you have this notebook so that you can review it. You have all the instructions here. And as I have said at the beginning, you are going to have this rosject forever in your account. Yeah, so this is already yours. You have a copy of this. So you are going to be able to open it and revisit it whenever you want. All right. So, so yeah, then let me know if there are any issues. You have been able to get the rosject properly. Have you opened the rosject properly? Yes, no. If there are no issues, then I can get it started. I'm going to get started with the class. So, Wilco, hello Wilco. Wilco Bonestro says yes, that is working. Perfect, excellent. Then let's get started. So the first thing that we are going to do is to start a simulation, a ROS2 simulation. Yeah. So we are going to be working with a simulation of this robot, which is a Neobotix robot. The model, if I'm not wrong, is the MP400. All right. But yeah. In order to start this simulation, all you have to do is to run this command. So in order to execute a command, we need to have a terminal, a shell, right? So the first thing we need to do is to open a new shell. Yeah. Then for this, you have to click on this first icon that you have here in the bottom bar. This first icon, as you can see here, it says web shell. So if you click here, this is going to open a brand new empty shell This is a regular Linux Unix shell. So you can type Linux commands. And in this case, what we are going to run is this script, this SH script, that I'm going to show it to you in a moment, but it just contains some basic commands and ROS2 commands to start the simulation. So let's copy this command here from the notebook. You can copy directly from the notebook by selecting it, selecting everything, copying, for instance, with Control-C, with the shortcut, and then pasting it here into the shell. You are going to see that the command starts executing here. So let's wait a few seconds. Don't worry if you see these red messages, just ignore them. As you can see also, a gazebo window has automatically opened here. Then, due to some bugs in Gazebo and sometimes the first time that you try to start the simulation, you might get you might get it working. Okay, in case that it launches properly, you are going to see something like this world with the robot here. Okay, but maybe you can get GC client stuck, like in my case here, it looks stuck. I'm going to wait some more seconds to see if it finally loads. Or another issue that sometimes happens is that the world loads, but without the robot. Okay, this might happen. If you get some of these issues, all you have to do is just to restart the simulation. Okay, so you can come. Let me put this here. You can come here to the shell. Just Control-C here to terminate the command, and then just relaunch it again. Okay. And now this second time, it should work okay. There you go. Okay, see, so now it has worked properly. I have the robot here in the world, as you can see. We have this world with these cones here and these barriers. Okay, and here in the center we have the MP400 robot from Neobotix. Okay, so you should have something like this after executing the script indicated here in the notebook. Yeah? You should have something like this. Then what we are going to do right now is to open the code editor. Okay? The code editor is this second button that you have here, right by the side of the web shell icon. Here you can see it, code editor. So if you click here, you are going to open here a window with the code editor, okay? This is important because it's going to give you graphical access, a graphical interface in order to interact with all the workspaces, folders that you have in this rosject, all right? Then in this case, for instance, what we can do is to have a look at the script, right? So if you see here the script that you have executed, it's this one, start basic neobotix sim.sh, and it's inside the Neobotix ROS2 package, which is inside the ROS2 workspace. Yeah, here you have the full path to this script. So if we open here the ROS2 workspace, we go inside the src folder, and here we go inside Neobotix ROS2. You are going to find here different scripts. In this case, the one that we have executed is the basic Neobotix sim. So this one, the first one here, start basic Neobotix sim. So if you double click here, you are going to see here the file opened, and you can see here exactly what commands we have executed, okay? Not important in this case, but in case that you want to investigate a little bit what we are doing here, you can do it like this, yeah? So as you can see, basically we have a ROS2 launch command here, which starts the simulation. So we are working in ROS2, yeah? This simulation is working with ROS2, and more specifically with ROS2 Galactic, yeah? So this rosject, if you click here in the name of your rosject, you are going to see that the distribution that you are using is ROS2 Galactic, okay? Yep, so far so good. Have you been able to start the simulation properly? Any issues? Yes, it looks okay, says Wilco. Perfect. Perfect then. Okay. My simulation is still loading. Says Alex Pam. Omaima says yes. How long has it been loading, Alex? If it has been loading for several minutes already, then what I would recommend you to do, Alex, is to terminate here the command. Okay, I'm going to do it myself. So you can terminate here the command where you are running the simulation with Control-C. Okay, Control-C, you terminate the simulation shell, and then you can run again the command, and it should load okay this time. Yeah? Sometimes the first time that you start it, as I said at the beginning, there are some issues related to Gazebo, but after you restart and you relaunch the command, it should work okay. Yeah, as you can see, it loads very fast now. Okay. So, yes, then, yeah, so for this class, it would be good that you have some basic knowledge on ROS2, like so I'm going to be skipping some parts like how to create a package, how to create a subscriber, a publisher in ROS2, etc. So I'm going to be skipping some basic stuff related to ROS2, okay? But in case that you don't have this knowledge and you would like to get it, I have left here in the notebook a link to our ROS2 Basics in 5 days course. So you can click here and you're going to be redirected here to the ROS2 Basics in 5 days, the Python version course. Yeah. So this course is going to provide you with all the basic knowledge that you need to have in relation to ROS2. Okay. Then let's already get started. So we are going to start by running a program. Okay. So here, if you come to the code editor, you are going to see that in the ROS2 workspace, basically we have 3 main folders, Neobotix, ROS2, and T3 Foxy. These two, you can forget about them because they are related to the simulation. So they are here in order to be able to launch the simulation, okay? But actually the package that we are going to be working with during this class is this one, exercise 3.1 package. Yeah, this is the package that we are going to be using and we are going to be modifying and adding things to it during this class, all right? So right now, as you have it right now, you are going to see that you have a Python script here inside the exercise 3.1 package folder. You have a Python script here. So let's open it with a double click. You can open this script. You're going to get it here. And you have also a launch file. Yeah. So if you open here the launch folder, you're going to see that you have a launch file here, exercise 3.1 package launch file, .launch.py. You can also open it, okay? So, yeah, this launch file, basically what it is doing, as you can see, is to just start an executable, exercise 3.1 from the exercise 3.1 package. So basically, it's running the executable generated from this program, from this Python script, exercise 3.1.py, okay? Then we can have a quick look, okay? I'm not going to go into too much detail, but we can have a quick look at this script. So yeah, first of all, we have some imports that we are going to use. Then we are defining a new class, which we are naming control class, which inherits from Node. And then here we find the constructor. In the constructor, we are initializing some variables, as you can see, but the most important thing is that we are creating also 2 subscribers here. The first subscriber, which is this ODOM sub, it's subscribing to the ODOM topic, yeah? And of course, it has a callback associated to it, this ODOM callback. Then I am defining also a second subscriber, which it's here, named scan sub, which it's subscribing, it's creating a subscription to the scan topic. And of course, it has another callback associated to it, yeah? And then finally, we are creating also a timer object, yeah? We're creating here a timer object which has yet another callback associated to it, timer callback, yeah? So basically, we have 3 main callbacks here. The callback for the odometry subscriber, the callback for the laser or the scan subscriber, and the callback for the timer, okay? Then here, the first 2 functions, we have the definitions for the sensor callbacks, the callback for odometry, and the callback for the laser, yeah? And inside here, we are basically saving some data, and we are also printing here, using the logger, some messages, yeah? So every time that the odometry callback is triggered, we are going to get a message, a log message, saying ODOM callback. And the same with the scan callback, okay? So we are going to be able to identify when our program is entering these 2 callback functions, ODOM callback and scan callback, okay? Then we have some support functions here, yeah? We have a function to get the front laser data, a function to get the yaw, the rotation of the robot. What else? We have a function here to transform transform quaternion to Euler angles. Yeah, interesting super function. Then we have another function here to stop the robot, which, as you can see, it's setting the velocities to 0. Oh yeah, so besides, I didn't comment this, but besides the subscribers and the timer, we are also creating here a publisher, yeah? So we are creating a publisher object which publishes messages into the command belt topic, yeah? So as you might already know, the command belt topic is used for sending velocities to the robot, yeah? Then in our class, we have some functions in order to stop the robot, setting the velocities to 0, to move the robot straight, setting the linear x velocity, and to rotate also, yeah, setting an angular velocity. And inside this rotate function, we have an important and interesting part, not for the code, but for the exercise that we are going to be doing during this open class, yeah? So inside this rotate function, we have a for loop here, yeah? But we are going to come back to this later. And then finally here we have the timer callback. The timer callback basically contains the main logic of my program, yeah? So as you can see, we are going to be checking here the value of the front laser message, yeah? Then so if this value is lower than, if this value is not lower, so is bigger than 0.5, I'm going to call the move straight function. So I'm going to be moving the robot forward, yeah? Else, so if this value is lower than 0.5 meters, this is in meters, then I'm going to stop the robot and call the rotate function, okay? And then finally, we have our main, where we just spin the node. Okay? There is your pairing. I know this is off topic, but is there a chance you can go over for our leader robot ROS challenge of the week 7, but using the new TF2 package and using Noetic? I'm having a hard time migrating code. Okay, no idea of what you are talking about right now. What is this challenge of the week 7? I don't know. Well, in any case, for today, it's not possible, Joe. So today we are going to be doing this open class, which is already prepared. So I cannot go over other things. Maybe you can write a post in our forum, clicking here in the yellow interrogation mark here, and post there a message commenting this, or even in the YouTube video. Okay, so after this class finishes, this class is live, of course, but after it finishes, we are going to publish the whole session as a YouTube video. So maybe you can leave a comment there, so me and my colleagues can check your message later, because right now I don't know what this challenge of the week is, so no idea. All right. Then, yeah, so this is the code that we are going to be starting with. Okay. Then, as you can see, it's a code which it starts to get a little bit complex. So we are combining publishers with several subscribers. We have several callbacks being executed at the same time, etc. Okay. So let's run it and let's see what happens. Okay. This is the first thing that we are going to do. So in order to run our program, we have to execute this command here. So let's open a new shell, okay? Don't close this one, leave it running, because this shell is the one which is keeping alive the simulation, okay? So if you close it or you stop it, the simulation is going to die. So we are going to open a new shell like this, and we are going to start working on this new shell, okay? Then, so yeah, what we are going to do now is to execute our program and see what happens. Yeah. So let me come here, copy here from the notebook this command and paste it here, and then execute it. There we go. Then let me have a look at the simulation and see what happens. All right. So here we can see that the ODOM and scan callbacks are being called. The robot is moving forward, as you can see, which is expected. And then when it gets too close to the object, then it starts rotating. Okay, but there is an interesting behavior here that we are going to check in a moment, okay? Yeah, so here it's rotating a second time. And now it's going to stop rotating and keep moving forward. And again, I start getting this. Okay, so let me stop this right here. And you will see that your robot keeps moving forward, okay? So don't panic, don't worry. In order to stop it, you have here some nodes, yeah? So you can scroll a little bit down here into this node section, and then here you have a command that you can execute in order to stop the robot from moving, okay? You will see that after executing this command, the robot is going to stop moving, okay? Then let me go back to the shell to get here all the logs. Okay, so this is the interesting part, yeah? So while the robot was moving forward, right, we can see that we are triggering the two main callbacks, odometry callback and scan callback, right? Also the timer callback. Yeah? So I keep triggering all the callbacks. The odometry callback, the scan callback, yeah, here we have a scan callback, odometry callback, and the timer callback. Yeah, of course, the frequencies are different for each one of them, but that's another story. Then, at some point, yeah, in my main logic, the robot gets closer than 0.5 meters of this ball that we have here in the simulation, right? And then we call the rotate function. Then as soon as we enter the rotate function, the robot, of course, starts rotating, and then it gets inside this for loop for 10 seconds, okay? And it stays inside this for loop for 10 seconds, as you can see here in the shell messages. Yeah. So here we enter the rotate function, and then we start getting the sleeping messages like we have here with the logger. Okay. But the interesting thing here is that while my program is inside this for loop, the other callbacks are not being executed, right? So meanwhile, my robot is doing the rotation for 10 seconds, as you can see right here. The other callbacks are not being triggered, yeah? Then as soon as the for loops ends and I get outside this for loop, I start getting again all the callbacks. Scan callback, odd-on callback, and of course the timer callback. Okay, so can somebody tell me what's happening here? Do you have any idea of what is happening? Yes, no? So basically, saying it simple, Wilco says, we are waiting and sleeping in the callback function. Not exactly. So what is happening, Wilco and everybody, what is happening is that my code is stuck here in this for loop for 10 seconds, right? And meanwhile, my code is executing these for loop, the callbacks, this callback and these two callbacks, odd-on callback and scan callbacks, are being blocked by the main thread because my thread is occupied executing this for loop. Yeah? And meanwhile, it is here, the rest of callbacks are not being executed. Right? Yeah, so we are using a single thread here. And this thread is blocked by the for loop. So the rest of callbacks cannot be executed. Okay? And this is a problem, right? So this is a problem for when working with robots. So for instance, here I am blocking the sensor callbacks. So my robot is not getting the updated data of its sensors. This is not good, as you can imagine, for a robot, okay? So we have to be aware of these kind of situations, okay? Especially when we have programs which are complex and are handling multiple callbacks, etc. Right? But isn't rotate called from the timer callback function? Yes, exactly. Rotate is called from here. What do you mean? It is waiting in the callback function. Well, so first of all, there are three callbacks here, okay? One is this timer callback, which is handling the logic of my program, and we have two other callbacks here, which are ODOM and scan, okay? Then my timer callback, it's supposed, as per the definition, it's supposed to be executed each 0.5 seconds, okay? So 2 times per second. 2 times per second, my timer callback function should be activated, okay? Then, this is happening, and this is being, this is working normally while I am moving straight, okay? Because I call the move straight function, I publish the velocity, and then I go back to the main callback function, I skip this, and I start again. I come back again here, okay? So no problem. The problem is that when we enter into the else statement, and we enter the rotate function, then we are getting inside here, and then my thread, the thread of my program is stuck here. It's not exiting this rotate function. And therefore, it's not being able to execute neither this callback function, neither this one, and neither it can execute this timer callback at the expected rate. Yeah? Do you get the situation? So the flow of my program is being blocked by this rotate function, okay? And this is not good, okay? As you can imagine. Then, okay. So in order to handle this type of situations, in ROS2, we can make use of executors and callback groups, okay? These are two different things, but they are related in the sense that these elements, both executors and callback groups, are going to allow you to modify how your program is going to handle and execute callback functions, okay? So they are going to help you in controlling the execution of callbacks, yeah? So the executors are responsible for the actual execution of callbacks, and the callback groups are used to enforce concurrency rules for callbacks. So basically, executors are going to define when my callbacks are going to be executed, and callback groups are going to define how my callbacks are going to be executed. Okay? Then, as for executors, we have two types of executors. We have the single thread executor, which is basically it's going to execute and run the callbacks in a single thread. And we have the multi-thread executor, which basically is going to run the callbacks in multiple threads. Yeah, as the name itself says. Very self-explanatory. And as for the callback groups, we have basically two. The reentrant callback group and the mutually exclusive callback group, okay? The reentrant callback group allows you to execute callbacks in parallel at the same time without restriction, okay? So you can execute multiple callbacks at the same time in parallel, okay? And as for the mutually exclusive callback group, it's the opposite, okay? So you can only execute one callback at a time. One callback, and then when this one finishes, the other one, and so on, okay? Then, so these are the main callback groups and executors provided by default by ROS2. Then it is worth mentioning that you can create your own, okay? But This is a much more complex topic, and we are not going to cover it here, but you can even create your own executors with your custom functionalities and your own callback groups as well. Okay? Then, what are we going to do? So we are going to create a modified version of our program. Okay? We are going to change some things here and see what happens. All right? So for this, let's create a new Python script. We are going to name it exercise32.py. Okay? So we are going to come here to our package, and here inside the exercise31_package folder, we are going to create a new file. Okay? Well, you have in the notebook here, you have. Oh no, you don't. You have not. Oh yeah. Oh no. Okay. Yeah, so let's create all this using the code editor, okay? So we are going to create this new script. Then, in order to create a new file, you can right-click in the folder where you want to create your file and select new file. And then you just enter the name that you want. In this case, it's exercise32.py. And as you can see, the new file is created. Now, inside this file, we are going to copy and paste the code that we have here. Yeah? So you can come here to the notebook, select all the code here, everything. Let's select everything. Control-C, copy it, and then paste it here into my script. I don't know what is that. Yes? Okay, then let's have a look at what's going on here. What do we have in this script? So first of all, we can see that we are importing the new elements. So from RCLPy callback groups, we are importing the two callback groups, reentrant and mutually exclusive. And from RCLPy executors, we are importing multi-thread executor and single-thread executor. Okay? Then, first of all, we have a change in the structure. So we have divided the code in two different classes. We have one class here named subscriber class, and down here we have another class named publisher class. Yeah? Then in the publisher class, we define the publisher for the command belt topic, and the publisher support functions. Yeah, like stop robot, move straight, and rotate. And then in the subscriber class, I define the subscriptions for the odometry, for the laser, and also my timer. Okay? Then, as for the publisher class, nothing changes here. Okay? No difference here. And then in my subscriber class, first of all, we can see that we are defining a new group here. Self group, we are defining a new group, which is of the type reentrant callback group. Then, in my subscriptions, in the odom sub, for instance, I am specifying this group. So this subscription is going to be part of the callback group, self group, which happens to be a reentrant callback group, as I have defined it here. Okay? The same I do with the scan, with the laser subscriber. Also, I am adding this subscription to the callback group, self group. And also, I am adding my timer callback to this callback group. Okay? So my three callback functions for odometry, laser, and for the timer, I am adding them to my the callback group, self group that I have defined here, which is of the type reentrant callback group. Okay? So this is the first change. Okay, so I am adding a callback group to my subscriptions, and then the other change comes here in the main. Okay, here in the main function of my script, as you can see, I am defining an executor. In this case, I am defining a single-threaded executor. Okay, I define my executor, I add my two nodes, the subs node and the publisher node, and then I spin my executor. Okay? All right, then let's keep advancing. Let's keep building our example. Then the next thing that we are going to do is to create a launch file for this. So in this case, you can create it with the commands. You have the commands here to create it, or you can just create it again using the code editor. I'm going to do it like this. So inside the launch folder, right-click, new file, and create my new launch file. And then again, copy and paste the code for the launch file. There we go. And what else? Yeah, and also, of course, I need to create the new executable. Yeah. So in order to generate a new executable from my new script, what you have to do basically is you have here the whole setup.py file, but actually what you need to add is only this line here. Yeah. Inside the entry point console scripts, this first one, you already have it. Yeah. So if you come here and you open the setup.py, you are going to see that here you already have this entry point. And then what you have to do is to add this second one, yeah, which is going to generate an executable. I'm going to copy only this line and add it down here. So we are going to generate here this executable from the new script, exercise 3.2, that we have just created, okay? And that's it. So now we are ready to compile. So let's follow the instructions here for compiling. We have to come here. Well, before anything, what I'm going to do is I'm going to execute this command that you have here in the notes. Again, if you come here to the notes, where you have the command to stop the robot, down here you have a command to reset the simulation, okay? So you can run this command, and what is going to happen is that the robot is going to get back to its initial position and everything, so that we can restart the example in the same conditions as before, okay? So let me execute this command, and you will see that the robot gets back to its initial position here, okay? All right, and now, yes, what I'm going to do is to compile my code. So let's go to the ROS2 workspace in order to compile, and callcom build. Yeah, callcom build is the command to compile in ROS2, and we are going to compile our package. There we go. Okay. Source, install. Very important to source, also after compiling. And then, at this point, we are ready to execute and run our new code. Yeah, so we are going to execute our new code, exercise 3.2, with its corresponding launch file. And let's see what happens this time. Okay, so let me execute the code right now. Again, the robot is going to start moving forward. And when it gets close, okay, so here it has entered the rotate function. Let's wait until it gets out. And now it gets out. Okay, so let me stop it right here. Let me stop the robot again by repeating the command. Okay, robot stopped. And let me reset also the scene now that I am here. Okay, so what has happened with our new code? So if we go back here to the log messages and we have a quick look, we are going to see that initially we have all our functions being executed, right? The timer callback, the ODOM callback, and the scan callback, all of them are being executed, right? Then as soon as I enter the rotate function, again, for 10 seconds, my callbacks are blocked. And once I exit the rotate function, my callback functions are again executed. So basically, I am having the same behavior as before. I have not fixed anything. Even though I have added my executor, right? Even though I have added an executor and I am using callback groups. So why? Why is this still happening? Why my code is being, my callbacks are being blocked when I enter the for loop? Can somebody tell me what's happening here? There is still one executor, says Wilco. Not exactly. So the word that you are looking for is not executor, but thread. There is still one thread. So we are using one executor, but the executor that I am using is single-threaded. So we still have one thread. Yeah? So even though I am setting my callbacks to be part of a reentrant callback group, remember that the reentrant callback group allows the execution of callbacks in parallel at the same time. But of course, this is not going to work. It has no effect as long as I keep using a single thread, right? So if I want to execute multiple callbacks in parallel, I need to have multiple threads. Okay? If not, I am going to have the same problem. Yeah, so my thread is going to be blocked. Yeah? Then yeah, so we can try to fix this in our exercise, okay? And basically, if we want to fix it, we need to use a multi-threaded executor, okay? So, for instance, in this case, we can try to use here a multi-thread executor. So here we are supposed to create a new script, exercise 3, but I am going to do the modifications here right on the same script, okay? Just to save time and not create more files. So let me copy this line here and let me comment this one here from my code, okay? I'm going to comment this out. And add here this. So instead of using a single thread executor, I'm going to use an executor of the type multi-threaded executor. And I can specify here the number of threads. So for instance, here I'm going to set 6 threads, okay? So you have to specify as many threads. So you have to provide enough threads so that the callbacks can be run in parallel, okay? So I can add here a multi-threaded executor, provide a number of threads of 6, for instance, which should be enough to handle all the callbacks. And yeah, and that's it. So let me recompile everything. I have already this, so I'm going to recompile, only adding this modification. Then another thing that you can do to make, so you need to make sure that you can handle different threads. So for instance, here you have a quick command that you can check to see how many CPUs your computer has. Okay? Okay. I'm not going to do it right now, but you can check it on your own, okay? So, yes, let me just recompile this. There we go. Lily is asking, when is single-threaded executor used? When is single-threaded executor used if the behave is the same? Well, a single-threaded executor can be used, for instance, with mutually exclusive callback groups. For instance, okay? So you can still work with multiple callbacks in one single thread, okay? The thing is that you are not going to be able to execute them in parallel, okay? So you will execute one first, then the other one, then the other one. So you have to have this control of when your callbacks are going to be executed. But you can still execute multiple callbacks using a single thread. Yeah, and executors have other advantages, like for instance, you can add multiple nodes to one executor. See? And others, okay? But yeah, so let me source this and run it again here, and let's have a look at what happens now. Okay, so robot is still moving forward. And now my robot is already rotating, but as you can see, it still keeps executing all the callbacks. Okay? That's why the behavior is changing a little bit. Okay? So now my code is not blocked by the rotate function. So let me stop the robot here. There we go. And reset the scene. Okay. Yeah, and we have here, if I'm not wrong, another example using mutually exclusive callback groups with different groups for each one. Okay. So yeah, I can add it here very quickly, but basically it's going to be the same. But what I encourage you here is that you do your own tests now. Okay. So I can show you this and compile it very quickly before we finish. And then we are going to create mutually exclusive callback groups, each one of them with a different group. And then each callback, we have to add it to one of these groups. So group 1, group 2, and group 3, for instance. Yeah, and then we can recompile here. Source, there we go. And then now if I run it, I should have the same behavior. Okay, so my code shouldn't be blocked by the rotate function. Yeah, there we go. So my robot is rotating now, but my callbacks keep being executed. Right? Okay, perfect. So let me stop this. Then stop the robot. Okay. Yeah, so basically I encourage you now, I have given you, so here you can read many more things, okay? So you have theoretical explanations here about all this, you can have a look. I have linked you also to the official documentation of execution and callback so that you can have a look. So I encourage you to keep working on this rosject, okay? So as I have said at the beginning, you have a copy of this rosject forever. Okay, this is very valuable. So you can keep working on this whenever you want. You can open now when the class finishes. You can open it next week, next month, or even next year. Okay, and I encourage you to keep doing tests. Okay, try different things. See what happens if you combine a reentry and callback group with mutually exclusive. See what happens if you if you change the number of threads that you're using. If you use a single thread executor with mutually exclusive, etc. Okay, so we have a limitation of time. We are already on 1 hour, so the time is very limited in here. But yeah, the interesting thing here is that you don't stop here and you keep doing your own test, investigating, and learning more. Okay. So on my mind is just, if I want to control more than one robot at the same time, I have to use multi-threaded executor. If you want to control more than one robot, not necessarily. No, it's not something mandatory. No. So you can control more than one robot using a single thread executor. The only thing is that you are not going to be able to do things at the same time. Okay? So first you are going to send commands to one robot and then to the other and then to the other. Is the only so you can, using a single thread executor, you cannot parallelize. Okay? Olivier is saying, in the past, the performance of the multi-threaded executor was thought to be less than optimal. So much so that some people have advocated for using multiple single-threaded executors. Yeah, so you have to bear in mind that using multi-thread executors and using multiple threads, it's going to, of course, consume more resources. So you have to bear this in mind, for instance, yeah? So for real-time applications, industrial environments, it's much more optimal to use single-threaded executors, okay? It's going to be much more fast and optimal, let's say, in terms of resources consumed. Yeah, then if you want to do it at the same time, then probably the option is to go with multi-thread executors, yeah. Or you can have a look at the ROS2 fleet management. Okay, so this is something very interesting that we are going to be releasing a course very soon on multiple robot management in ROS2. Okay, super interesting. We have also a summer school. So before finish, I have to finish now, but before finishing, let me just show you here a last link to our intermediate ROS2 course, okay? So all this is explained more in detail with more examples, etc. in the intermediate ROS2 course, okay? Which we published just some weeks ago, so it's very new. Okay, and here we are covering some aspects like this one, managing complex nodes using callback groups and executors, okay? And many other things which are not covered in the ROS2 basics course, like how to work with ROS2 with parameters in ROS2, or understanding what is quality of service, data distribution service, DDS in ROS2. Some interesting topics that are not covered in the ROS2 basics course, okay? And yeah, so for the ROS2 fleet management, okay? And yeah, for you have this very interesting application. This is the official ROS documentation. And this is very interesting, the fleet management in ROS2. Okay, so I encourage you to have a look because it's very, very interesting. And also, it's this also, the RMF, okay? This RMF. Super, super interesting, yeah? And also we are doing a summer school on this subject, okay? Managing fleets of robots with ROS2. Super interesting. So the first one is fully booked already, so it's sold out, but we will be doing more. So if you are interested, if you are interested on this, stay tuned for news. Okay, so yeah, I'm going to close it already here. Thanks a lot for being here with me in this open class. I hope that you enjoyed it, that you learned a little bit. At least you can take something from this hour. And yeah, thanks a lot. I will see you again next week, next Tuesday. And as always, until then, keep pushing your ROS learning. Bye-bye.